So following on from some of the tests I've been doing with spectrum analyzer and tracking generator, I thought I might do a quick video about how you match filters, because typically when you receive a part which is a filter, it might be a ceramic filter, a crystal filter. There are all sorts of different ways of doing filtering, but the one I used for this particular test was a crystal filter. The reason I used it is they tend to be quite narrow band, but one of the things is that they don't actually match to traditional 50 ohm impedances of test equipment. So when you're trying to test these devices, you need to have some sort of matching arrangement in there in order to get a real feel for what's going on. In fact, if you don't match them to 50 ohms, you're not doing yourself any favours. First of all, the response will certainly not be optimized, and second of all, you'll find that there'll be quite lossy in the pass band. These crystal filters are bandpass filters, and you might have 15 or so dB of attenuation if you haven't properly matched it. The other thing to note on this is that once you have matched them and got them to 50 ohms, actually when you put them into a circuit, it's unlikely actually that your circuit really will be 50 ohms, so just keep that in mind. So we're going to be putting a signal in here. It's going to be transforming into a different impedance on this side of the filter, and I'll come around the other side, and on the other side of the filter we've got a similar impedance. That in fact the filter is a reciprocal device, so in general you can turn them either way around and they should in theory be identical. In practice it's not quite identical because of manufacturing tolerances, but to all intents and purposes when you're designing you treat them as being a reciprocal device, and so there'll be a similar impedance on that side to that side, and so we need to do some matching to get to 50 ohm on the other side. So the tracking generator will go in here feeding a signal in, and the spectrum analyzer input will go here, and they're both 50 ohms. So the question is how do we match to this filter? Well, the first thing we need to know is what is the termination impedance of the filter. So here we go. As always, go for the datasheet. Datasheet is always your friend. And this particular device I got from DigiKey, and if I zoom in here you'll see it happens to be the first item on their list, and you'll see also that towards the right hand side, which I've got highlighted here, there's a termination impedance. So that's 1800 ohms in parallel with 5 picofarads. So what do we do with that? So here we go. Now I'm sure you were hoping that I wasn't going to go into the depths of Smith charts, if you ever heard of those, and so I'm not going to. You'll be glad to know that in this day and age we have online calculators to do the calculations for impedance matching, and very handy they are too. Although if you do have time on your hands and you want to learn how to use a Smith chart, please go right ahead. They're something that is probably wise to have in your back pocket, but personally for me these days I get lazy and just use calculators to do it all. So here's an example of one of the many calculators from this particular website, and this is an L-matching network calculator, and it's real easy to use. So what I'm going to show you here is that we insert a few figures into this box here. So there's a 50 ohm impedance, which is our source impedance here, and we also have leave the source capacitance and inductance blank because it's a straight 50 ohm impedance, and then our load resistance is 1800 ohms, and I'm just going to zoom out a little bit and you'll see there is quite a convenient circuit diagram here which shows what these items are. So we've got 1800 load resistance, and that was in parallel, if you remember, with 5 picofarads, so that's that, and we'll leave the inductance blank, we're not using that for this. Put in the frequency here, 10.7 megahertz. Now block DC, what do we want to do there? Well, this depends on whether or not you want to have a an AC coupled or DC coupled scenario. Now, it doesn't really matter in our particular case because the test equipment that we're going to be using is all AC coupled already. And in fact, on the solution that I used, I actually left it as no blocking of DC. You might find it a more generic case for RF circuits is to say yes, block DC, but that's just how I left it because it was of no consequence. And the difference is whether or not you have a matching network which is comprises of a capacitor inductor like this, or alternatively the lower scenario, as you can see, which that doesn't block DC from here. So if I submit that, and there's my answer. And if I just go up a little bit and we'll zoom in, and you'll see that it's provided me with the capacitance that I should be looking for in the matching circuit just here, and the inductance as well. So we'll use that and we'll put that in our matching filter. So here are the figures put into a circuit diagram from the website, and you'll see here there's a 4.4 microhenry on both sides, because if you remember I said that the device actually is a reciprocal device, so you need to put a matching filter on both sides, and if you want to match 50 ohms to both sides equally, these capacitance and inductance values will be the same on each side. Now, in practicality, if these work first time, generally you'll be very lucky. In practice, you quite often find you need to do tweaking. This is a lot down to your board layout and the parasitics. Not only that, you can't really get 4.4 microhenry inductors off the shelf. So in the end, on this particular design, I ended up on the breadboard that I used here, I used a 3.9 microhenry inductor, and I've used a 50 picofarad in parallel with a 3 picofarad, and that's what I found matched. And although you can do this with a spectrum analyzer with a tracking generator, in fact, if you have a vector network analyzer, you can tweak it a little bit more easily, because I mentioned the Smith chart earlier on. You can use that as a real-time way to be able to model this, and in fact in real time actually correct for it, which is actually how I found out the 50 picofarad in parallel with 3 picofarad. And I just used parts from the parts bin, and just tried a 4 picofarad at first, and then a 2, and then the 3 seemed to be the sweet spot, and apply it to both sides of here as well. So you'll find that if you adjust the impedance here, it has an effect on this side as well. So you can't just adjust things here, you have to adjust things really on both sides in order to be able to get a realistic outcome. Anyway, that's all about matching crystal filters. Many thanks.